Greetings, everyone. My name is Ocelot, and I'm one of the Mama Bears Brigade. And I'd like to just give you a little background of the nuclear age. Kind of was initiated when FDR signed in December of 1941 the order to start building the bomb and authorize the Manhattan Project. And the nuclear age was considered a utopian vision of what the world could be, and we now know how wrong that vision was. I mean, they imagined that it was going to solve all the world's problems, and what it has done instead is left us to confront as best we can, and from the grassroots up, I believe, the intractable problems that have been left and continue to be left by that supposedly utopian vision. And a lot of times we find ourselves confronted with very large scientific and technological organizations that claim an edge on knowledge and try to make it so complicated that those of us who are indeed affected and our children and grandchildren are affected, that we're unable to participate in the process of making decisions. And so that's part of what we're here for today, is to take some of that power back, because the results are falling on us and will for generations to come. In September 1981, 35 women, many from the Landite communities of the 1970s, set forth as an affinity group to help blockade Diablo Canyon nuclear power plant, along with 2,000 to 3,000 other people. And their action, whimsically and powerfully, consisted of staging a picnic at the gates, the Mama Bears picnic. Thus began Mama Bears Brigade. And they continued to be active and support each other in resisting nuclear energy. Many of those women moved on to other things. After the horrific accident at Fukushima, Mama Bears Brigade came out of hibernation with a few new members. Blue Jay was involved back in the original day, and we kind of picked up the torch. And incidentally, at that same point in September 1981 was also the time when women began walking from Wales to Greenham Commons to establish the largest and longest sustained feminist, or perhaps any other, anti-nuclear protest of the 20th century. They camped at the gates of Greenham Commons and continued acts of protest and civil disobedience through the 80s and through the 90s, is that correct? So the Mama Bears and WIND was part of that movement. I myself have been part of resisting uranium at the Four Corners since the mid-80s, when I was extremely active and continued to be active throughout the years, with a special concern for what happens in our Four Corners area. I'm from northern Arizona originally. I also want to say that as a child in elementary school, I had the experience that perhaps many of you have of having to duck and cover under your desks. I grew up in Florida, and we were just a stone's throw away from Cuba in the 1963 crisis. And I think once you experience that, you realize that you're kind of on your own. And what are you going to do about it? So the Mama Bears last summer, in consultation with members of the Havasupai tribe, on whose land the Canyon uranium mine that we specifically targeted south of the Grand Canyon sits, we established a peace camp within about a mile of that mine in view of the sacred site of Red Butte, did peaceful protest and education of the millions of visitors that come to the Grand Canyon in the summer. We are entirely grassroots, self-empowered. We believe we can all learn enough to speak out. We also exist entirely on donations and our personal resources to continue moving forward. So we're going to pass the basket at the end, and anything you can donate, I want you to know that it will go entirely towards publication, printing. WIND has been invited to support Navajo people in Cameron at a conference. These folks are living basically on a contaminated waste pile, and they've asked her to come up next week to do an educational presentation and bring her Geiger counters. So we're looking for funds for gas and to support that continuing work. So the Mama Bears Brigade, our motto is action is the antidote to despair. We believe that armed with vision, empowered with knowledge, and moving forward on the strengths of our hearts and each other, that we can change the tide and speak out for life to come. So we thank you.
Thank you. I'm going to start with the 7 links of the nuclear chain. Okay, that slide here, it's on page 2 of your handout. And basically, this is a simplified version of what happens and what has happened for many years now. And that is, uranium was discovered or noted as a new element in 1789. Okay? But they didn't know that it was radioactive for some time afterwards, late in the 1890s. So this chronology kind of deals with uranium mining first, and then, of course, you go on to uranium milling, and taking from the ore, you create a yellow cake. That's the milling part. Then it's enriched or processed after that in order to create a form of uranium that can be used in nuclear power plants, and then if it's further enriched, it can be used in nuclear bombs. Actually, most nuclear bombs now are made out of plutonium, because we have hundreds of tons of waste plutonium now. So, you okay, guys? I'm not standing on my back.
No, you're fine.
Okay, all right. And then very shortly, in the 1890s again, we had the discovery of X-rays and the beginnings of the use of medical radiation, which I'm only going to touch on a little bit, not very much. In the 1940s, of course, to the present, we've had the presence of nuclear weapons, but nuclear weapons came, I couldn't decide nuclear weapons, nuclear power, because you need a nuclear power plant in order to create the plutonium to make nuclear weapons, or in order to, but really nuclear power started after nuclear weapons were used as a commercial enterprise. It started in the late 50s, early 60s as a commercial enterprise. So, and then really we didn't start using depleted uranium weapons, which are a waste product of this whole chain, until later on, until really the 90s was when it began to be people became publicly aware that we were using this waste stream, because you have to enrich uranium, so there's a little chunk of it, actually a big chunk of it, about 98% of it is waste. Okay, so, and then of course we have the nuclear waste problem, which I'm sure many of you are aware of because of the news about WIPP and the waste isolation pilot plant in the corner of southeast New Mexico, which is continuing to leak small amounts of plutonium and americium today. Tiny amounts in the air. Okay, so what links all of these 7 parts of the nuclear chain together that we've been living with for the last 70 years, that perhaps we've been terrorized as children about nuclear bombs, or we've been worried about nuclear power, we've been worried, a lot of us have worked on some of these issues. And it seems to me that the main thing that links these together is the issue of low-level ionizing radiation. So, what scientists in the 40s and 50s started to do was try to figure out, well, it's clearly people are damaged. They knew from X-rays that people were damaged by ionizing radiation. People got burns and so on. And they began to do these studies of trying to figure out how much risk would come from such and such a level of exposure. And in the 50s, all of that work was within the secrecy, was kind of clouded by the secrecy of the Manhattan Project. So anybody who wanted to use nuclear weapons had to downplay the effects of low-level radiation, because, of course, if any of that was true, if it was really going to cause that much harm, you couldn't use nuclear weapons. Okay? And the same goes for all the other parts of the nuclear chain. If what the independent scientists have found about nuclear, low levels of of ionizing radiation, if that's true, then all of these 7 links of the nuclear chain can no longer function in the way that they are functioning now. There are basically 2 models that have developed really since about 1958. Okay? In 1958, an Oxford professor named Alice Stewart published what at that time was really controversial, and she found that if any pregnant woman was X-rayed during pregnancy, her child had a 50% chance, a greater chance of getting leukemia in their lifetime. Okay? And this was appalling to the nuclear authorities. They thought she was really out of her mind, that she had done something wrong, her research design something, but it couldn't possibly happen at low levels, that those low levels of ionizing radiation, this couldn't possibly be the effect. And basically that's been their response to enormous amounts of independent science about low-level radiation ever since 1958. And they've gotten better and better and better at hiding and tricking the public about low-level radiation. So really, I want to focus for a good half of today's presentation about what the models are, the independent models. Okay? So I know people hate acronyms. Okay? So I'm only going to ask you to remember two acronyms today. Okay? One is ICRP. And ICRP is the International Commission on Radiological Protection. The International Commission on Radiological Protection, based in Geneva. So many of the national regulatory bodies, like the EPA, our Environmental Protection Agency, the Nuclear Regulatory Commission, and not just in this country, but in many other countries, they derive their idea about how much harm comes from very small amounts of low-level radiation. They get it from the ICRP. Okay? Now, that model is really derived from atomic bomb studies, and it's derived from a 50s approach from mainly physicists and mathematicians who were trying to create a mathematical model of, if you have this much radiation and it heats up water in this degree, then what effect is it going to have on tissue? So it's just kind of a model that's very abstract, very based in mathematics and physics, except for they related it back to the atomic bomb survivors. Okay? And there's a lot of problems with that study, so I don't have time to go into what those problems are, but there are a lot of problems with that. The ECRR is the other acronym I want you to remember. And the ECRR is the European Committee on Radiation Risk. The European Committee on Radiation Risk is composed of over 20 scientists from around Europe who have done hundreds of studies themselves and have also looked at hundreds of actual health studies, which show that not only is low-level radiation more harmful to human beings than the ICRP would like to admit, but that there are many other results from exposure besides cancer. Okay, there are many other types of health problems that occur over the long term. Now, so the problem is that every time we hear about radiation, so when the nuclear authorities and the people that speak about these things are talking about it from an ICRP perspective, largely. Okay? So we see, for example, when the first atmospheric plume from Fukushima was coming towards the United States and then crossed across the United States in the first 2 months after March 2011, all the authorities would say is levels are they're not levels of concern. Not levels of concern, nothing of concern, nothing of concern. And I want to show you today why there's that huge difference, that huge gap between the independent science and those people who want to tell us it's all okay. And when you read on the media, it's all okay. So I'm going to be talking about that huge gap between those two approaches and why that is and why that exists. Because if people can know this information, then you too can participate in breaking the nuclear chain around this issue. Okay. Yeah, I'm not really going to talk about the atomic bomb survivor studies except to say that they are flawed and they do give a too low a figure for the resulting cancers. Although they're still studying these survivors of Hiroshima and Nagasaki. Okay? So, and maybe many people don't know that the survivors who were children 70 years ago, they are now in their 70s, children are much more affected by low-level ionizing radiation. So even the people pretty far out of those cities, of Hiroshima and Nagasaki, those people who were children in 1945 are now dying of cancer. Okay? Many of them died before now, but many of them, cancer takes a really long time to develop after the initial exposure. So, yes, the United States dropped those bombs in 1945, but people are still dying from that. Okay? So I just want people to keep in mind that this is very long term. We need to have a very balanced approach to this because some people will tell you, if you get on Facebook and so on, some people will tell you, oh, this is the apocalypse, Fukushima is the end of the world, And it is and it isn't. I mean, really, if the end of the world started, it probably started in 1945. But it's been very, very slow. It's very slow. It's probably slower than we can possibly imagine. So we went to a presentation at Antigone Bookstore last night with a fellow named McPherson who's working on global warming. And he said, well, he expected because global warming is going to impact us so strongly that we only have 1 to 5 years left. Now that may or may not be true. I don't know for sure. I don't know the science of global warming as well as I know the science of low-level ionizing radiation, but I think that my impression is that really there's nothing that human beings can do that is powerful enough to completely eliminate life on this planet. Life is much more varietous and adaptable than that, even if it's just a little fish someplace, in a river is going to make it, okay? That's my hope and that's my belief, so I'll share that with you right now. I am on Break the Nuclear Chain, Defend Yourself with the Truth.
In the corner. What's the page number? Your page number. You have a different page number.
Okay, I am on. All right, I'm going to get on page 4. Let's go to page 4 here. Okay. All right. I'm going to just talk a little bit about the history of low-level ionizing radiation because it helps you understand what it is. People get terrified partly because you can't see it, you can't smell it, you can't hear it. So what is it? And in the 19th century, scientists like to experiment with a lot of things, and William Röntgen was experimenting with a vacuum tube, and he found that if you put electrical energy through this vacuum tube, it would create a situation in which the air would carry electric current, so the electrons were moving through that, and they discovered that these rays that came out of there you could see through like a human body, okay? And that was the origin of X-rays. William Röntgen, like many of the early scientists, died of radiation exposure. Henri Becquerel, who was in Paris, he was curious about Röntgen's experiments, and Becquerel wanted to find out if these rays or this energy that was very strange because, again, you couldn't see it, you couldn't hear it, you couldn't smell it, you couldn't perceive it with your 5 senses. He wanted to know if that energy could come out of rocks. He had a huge mineral collection at the Museum of Natural History in Paris. So he went through all of these rocks, and he, by accident, discovered that he had left some bits of uranium salt in a drawer with some photo paper, and it developed the photo paper. Okay? There were little spots on the photo paper in it. He realized that some of these rays were coming out that were not generated by sunlight. It was something within the uranium itself that was emitting energy that caused the paper to develop. Okay? So, and Marie Curie wanted to discover the source of these rays discovered by Becquerel. And her stroke of genius was realizing that that energy must come from the atom itself. Okay, it must come from the atom of uranium. She and her husband Pierre wanted to find out where this radiation was coming from in uranium. So they ordered a ton of uranium ore from Czechoslovakia. Czechoslovakia is where uranium mining first started. So you can imagine there they are in their little shed in Paris, and this truck shows up and dumps a ton of uranium ore in the middle of Paris. And she spent the rest, many years, several years after that, basically processing this ton of uranium ore by hand and getting to discover 2 other elements that were radioactive within that, and that was polonium, named after her native country, Poland, and radium. And so she was the discoverer of radium, which is another natural, uranium, polonium, and radium are all naturally occurring radioactive materials, but in the lab they concentrate them. In the enrichment process they're concentrated, they're not ore anymore. They're much more concentrated. Okay. Both Marie Curie and her daughter, Irene, who also got a Nobel Prize for her work in this field, as well as her daughter-in-law's husband, all died of radiation-related diseases. Okay. Rutherford, as an English scientist, And I just want to refer you to the next slide here. This is probably one of the most important ones here. And it just shows you a simple model of an atom, okay? And Rutherford, by a very simple technique, he tried to measure what kinds of rays, this strange energy coming out of the atom that nobody could see, what was it? And he discovered that there were different particles in the very center of the atom that would do different things. If you put a magnet on it, because they had different, positive and negative electrical charges, these little particles that came out of the middle of the atom. So Rutherford put a magnet up, and he realized that some had a positive charge, some had a negative charge, and some didn't have any charge at all. And these particles that are coming out of the middle of the atom, the nuclear scientists are really good at making this much more confusing than it has to be. What you really need to remember is that alpha and beta radiation are just different particles of the atom. Okay? Alpha is a little bit heavier. It's made of 2 protons and 2 neutrons. Beta is a high energy, just an electron, but it's not the electron from outside in the orbit of the atom. It's from the very center, from the very core, from the nucleus. Okay? There are also basically this gamma radiation, which is not a particle, but an emission of energy as the atom is breaking down. Okay? Unstable atoms release all of these types of energy. Okay? If you have a metal that's not radioactive, it's not releasing any of these particles. Okay? It's stable. The electrical it's in electrical balance, negative and positive. So I think because people, like in my experience, people's eyes glaze over when you say alpha, beta, and gamma. But it's really important to understand the difference, because the nuclear authorities use our ignorance against us to basically tell us it's all okay. Okay. And the other thing I want you to remember from this slide is that each one of these disintegrations, okay? So when an alpha particle shoots off, when a beta particle shoots off, each one of these disintegrations is called a becquerel, after Henry Becquerel, who discovered that uranium was radioactive. So when you hear becquerels, basically one becquerel, 1 disintegration per second. That's what a becquerel is. It's 1 disintegration per second. Okay.
I'd like to add, when there's a star on our blocks, that means it's one she's working with today.
Yeah, kind of, to some
Kind of.
extent. To some extent, yeah. Okay. All right. So they discovered that if you could shoot neutrons into a very dense atom, like uranium, it would split apart because it was so unstable. And when it split apart, it became basically about 200 other types of isotopes, about lots of other particles. So when we talk about fission, all they're talking about is splitting that atom and creating all of these other radioactive particles that are particles. And it also creates some of these gamma rays, which are rays. Okay? The most important thing I think that I can share with you is that most of the measurements about radiation that we have that are in public are external measurements of gamma. Okay? So X-rays are very similar to gamma rays. Gamma rays, like X-rays, go through the body and out the other side. Okay? And they can also cause damage, but they go through the body and out the other side. If you're talking about other particles, alpha particles and beta particles, they're frankly they're not that dangerous outside the body. But when you breathe them in, when you drink them, when you ingest them in any way, when you eat food that has small particles of alpha or beta particles in it, those particles can get stuck in your body and stay there for many years. So the nuclear authority model is largely based on external radiation. The ICRP model is based on these external measurements. When they studied the atomic bomb survivors, for example, they only measured the initial gamma energy and estimated that as their entire, what they call a dose. Okay? to me, dose sounds like medicine. This is not medicine. So I like to use the word exposure. So they didn't take into account any doses from contaminated foodstuffs in those studies. And they still don't really like to do that. They like to give you, like the WIP. A good example of this is the WIP leak that's just happening now. It started on the 14th of February. The authorities immediately came in and said, this is such a low level, it's not of any concern. Because they were talking about if you were, got a few becquerels from the X-rays aren't measured in becquerels, but if you got just a little bit of radiation externally, or you were standing near like 1 becquerel of plutonium, and you were standing near it, it's probably not going to cause you any harm. But that's not what's happening at WIP. Okay? So they're comparing basically internal particles like plutonium and americium, which is what's coming out of WIP. They're comparing those the potential for inhalation, those internal particles, with external, like he said, one of the spokesmen said, it's just like a chest x-ray, It's no more than a chest x-ray. Again, a chest x-ray is external radiation, and it goes through you and out the other side. And it's not like breathing in a particle of plutonium which stays in your system, even if that particle of plutonium has a lesser amount of radiation than the chest x-ray. So these are one of the ways that the nuclear authorities continue to try to, I think, deceive the public, and that deception has emerged from a very secretive period in our history, and it hasn't really opened up yet. That's just an example. So to give you the best idea of what the difference is between external and internal, one of the best analogies I ever heard was, imagine that you're standing next to a fireplace, okay, and you're warming yourself at the fireplace. You're getting external energy from that fire. Okay? It's going to have a very different biological effect if you reach into the fire, pull out a coal, and eat it. Different. Okay? That's a really good analogy for the difference between external and internal radiation. Okay. Some of you may not know that also the secrecy around these health issues with low-level radiation is exacerbated because in 1959, the World Health Organization signed an agreement with the International Atomic Energy Authority. Sorry, I told you I wasn't going to give you any more acronyms. But basically it means that it's very difficult for the World Health Organization to do any honest studies that don't promote nuclear power. So there's a lot more information about that. There's a whole group called the Independent WHO, or the Independent World Health Organization, and you can find out a lot more about that particular issue from them. But it just, again, we're going to skip over the decay chain, this radioactive decay chain. What page are we on there? What page is that on there? You're on, we're on 6, on page 6. I'll just mention in passing that when these atoms disintegrate, they change into something else. So it's not as if disintegration just takes the radiation away. What we have in Chernobyl today is a situation where in northern Ukraine, plutonium is disintegrating and the amount of plutonium is getting lower, but it decays into americium-241. So the americium is increasing. And Chernobyl happened in 1986. Okay. That's just an example of what they call a decay chain. And again, this situation, low-level ionizing radiation, I don't know how many of you have ever heard or read in a newspaper a nuclear authority saying, don't worry about whatever it is, Fukushima, don't worry about Chernobyl, don't worry about WIP, because you get more radiation from a banana, or an international airplane flight, or eating Brazil nuts. Okay? Or TV, all the time. Yeah. TV, by the way, is not ionizing radiation. It's a radiation, but it's not ionizing radiation. Ionizing radiation means that it has the power to knock electrons out of molecules. It has the power to knock electrons out of other compounds, out of other atoms, out of other things, and cause way more damage. I mean, the cell phone, unless, everybody has a cell phone. It's emitting radiation, but it's not ionizing radiation. It can still be damaging. It can still, in some cases, cause cancer if you hold it to your brain for long enough. but it's not as damaging as ionizing radiation, okay? Because it goes through your system and out the other side, and it doesn't have that same amount of power. It depends, you know, when that illustration of the atom disintegrating, those particles come out of the center of the atom with so much energy, millions of electron volts in the case of alpha particles. Rosalie Bertell said that these particles, when they come out of that atom and they knock into, say, an electron in some other molecule, say inside your body, they knock that electron out of orbit around its own nucleus with sometimes the same amount of energy that it would take to knock the Earth out of orbit from around the sun on a grand scale. But it's happening inside your tissues if you happen to inhale or eat one of these small particles. Okay. And I put that one slide again in here of just the disintegrating atom, because I want you to note here that the alpha is coming out. These particles are just shooting out with that enormous amount of power. They're shooting out of the atom. Okay? Again, if you're sitting there and you have like alpha and beta over here, it's not going to cause much harm because alpha can be stopped by a piece of paper, which the nuclear authorities always like to remind us, alpha radiation, you just stop it with a piece of paper. Okay? But look what happens on the very next page if you get an alpha inside your lung. I don't know if you can see this very well. But so it says plutonium particle in ape lung tissue.
It's page 7.
Page 7. It's on page 7. And there's a little, I don't know if you can see it, I have a couple illustrations of this because this is really crucial for understanding internal radiation. And that is, there's a little black star here in the center. This is called an alpha star. This is an illustration of a particle of plutonium in ape lung which has been radiating, that is disintegrating. Basically radiation is atomic disintegration. So it's been disintegrating and it caused the death of so many cells in this ape lung that you've got this small little area of dead lung in a star shape. Okay. So all of these elements that are created in fission, like strontium, plutonium, have also, many of you know, very long lives, many of them. If there are 200 different kinds of elements that came out of Fukushima and Chernobyl and 3 Mile Island when they melted down. The nuclear authorities pick a few of these, like cesium and strontium, to talk about. They don't really like to talk about too much about plutonium. We had months before we had our first plutonium readings from Fukushima, even though it was released in a few hours. Okay. But they're very long-lived. What I was going to say is that some of these particles that are released, some of these elements that are released, live for a few seconds. Some of them live for a few minutes. Some of them live for a few days. That is, they continue radiating. They continue disintegrating. Iodine-131 is one that we hear about a lot. It was released in both Chernobyl and in Fukushima. Iodine-131 has a half-life of only 8 days. Okay? Cesium-137, which was released from all these meltdowns, one type of cesium has a half-life of 30 years. Okay? Now, what does half-life mean? Here's another one of these really, these nuclear industry attempts to confuse you. Okay? Let's not buy it. Okay? Half-life doesn't mean that's as long as it's radioactive. Okay? Just one of these scientific physics ways of telling you that it takes 30 years. If you had 100 pounds, God forbid, 100 pounds of cesium-137, in 30 years you'd only have 50 pounds. So it takes 30 years for half of it to decay. But don't let their terms and their measurements confuse you, really. I think they do this on purpose sometimes. I mean, if you can imagine the numbers of ways of measuring radiation since 1945, they've had like 16 different words and different ways of measuring it in different circumstances. So you get Rem and Gray and Curie and Becquerel and so on, lots of other ones. I'm not going to confuse you with all that right now. I'm just going a lot of us just like to stick to becquerels, because that's an actual physical measurement of disintegration. 1 becquerel is 1 disintegration per second. That's a good thing to remember, 1 of those radioactive disintegrations per second. The next slide has another, maybe harder to see, but more of the little alpha stars. Okay? Now, this is about 5 microns. Alpha particles like plutonium travel about 5 microns inside tissue. A micron is a millionth of a meter. These are very tiny, very, very tiny amount of damage, but it's still an assault inside the cells. Okay. Beta particles are lighter and they travel a little further. So they might travel about 10 or 15 microns. Okay, but they're still causing damage to the inside the cell. Okay. On the next page you have this one here. This is on page 8. Okay, on page 8, there's an amazing scientist who's worked on Chernobyl named Bandashevsky. And he, kept hearing, like the World Health Organization, I think, says about 30 people died at Chernobyl. Okay? This is how the ICRP works. All right? Really underestimates. But Bandashevsky, he did a measurement where he measured exactly how much cesium was inside the bodies of children, because cesium was released all over, very contaminated, and people have been eating cesium in their food. Tiny, tiny amounts, just a few becquerels of cesium in their mushrooms or in their, spinach or something since 1986. And he found that the higher the level of cesium in the bodies of these children, the more they had heart problems. So they have what they call Chernobyl heart. They have heart disease. And this is one of the reasons why they have heart disease. And it's because cesium-137 inside heart tissue, okay, is disintegrating because it's radioactive. It's disintegrating inside the heart tissue. And these darker areas are one of Bandashevsky's slides of heart tissue, which have been, many of the cells have died off. Okay. Okay, great.
You can.
Yeah, I think I'm doing okay. I'll quickly move over this funny slide here with all the lines on it. Another problem with the nuclear authorities, the regulatory agencies that we have, like the NRC, the EPA, IAEA, and so on, they're very slow to take in new science. Very slow. One of the things about the new science of uranium is that might explain another reason why the health effects are so much higher than what the ICRP model would say, is that uranium and all heavy metals act as antennae. They attract what are normal cosmic rays. Okay? Even in this room right now, we're being radiated from outer space. There are normal cosmic rays that are that occurred at the Big Bang, occurred at the beginning of creation, and those rays are still coming down to Earth. Okay? And we're still, but usually they go through our bodies in a very random way. We have recently discovered, within the last 15 years, that heavy metal particles will concentrate those rays. So they're no longer going through the body in a random way, but they are attracted to that particle of uranium or that particle of plutonium or some heavy metal that's stuck on a bone or on a heart cell or on a whatever. And it will magnify the effect of that radiation as well.